So today we're going to do one more problem on voltage, and we're going to say, okay, Mr. Saba is at point B. You know me, I love to pick on poor Mr. Saba. And there's two charges. In this situation, however, the charges are not equally distant or equidistant from point B. Q1, this positive 50 microcoulombs, is much further over. But we have enough information to find the distance. We know the legs of the triangle. It turns out this is 30 centimeters and that's 30 centimeters. They're equal. So it's an isosceles triangle. And to get the distance, it's just a hypotenuse using Pythagorean theorem. So 30 squared plus 30 squared. Don't forget to take a square root. This is 42.4 centimeters. And that makes sense. Now the other charge, the negative 50 microcoulombs, is much closer. So its distance will be not much closer, but it's going to be a little closer. It will be the Pythagorean theorem, but we're going to use 30 squared, and the other leg is 20 squared. And let's see what we get. 36.1 centimeters. So from here on out, we're going to just do the two voltages. So we've got V1 is KQ over R, and the K is 9 times 10 to the 9th, and the Q is 50 microcoulombs. Micro is 10 to the minus 6, and the distance is 42.4, times 10 to the minus 2, because it has to be meters, which is 0.42. I won't forget that on the next one. And it's going to be a big number. Yeah, 1.06 times 10 to the 6th volts. On the other side, we remind ourselves that we do need to worry about that negative charge. So 9 times 10 to the 9th, negative 50 times 10 to the minus 6th, all over 0.361 meters. I'm not going to forget to convert it this time. So crunching it out on our machines. And we should get a higher voltage. It's not surprising. Oops, I think I put something in wrong. Let me just double check my numbers. Yeah, 1.25 times 10 to the 6th volts. And that's negative because it was a negative charge. So the V at point B is V1 plus V2. 1.06 times 10 to the 6th. Now we end up subtracting because the negative is higher. And we get negative 1.85, 1.86. Oops, there's my 6 times 10 to the 5th volts. So the bottom line on this is that the negative charge wins because it's a bit closer. So overall, at that point, the voltage would be reading as negative. What we're going to introduce today, we probably won't get into any of the math, but that's okay. We'll do that in the next video, is something called capacitors, which are also called condensers. So if you've ever heard of a condenser microphone, if you can buy them, that's just a capacitor microphone. It's just another alternate name that they use. So what capacitors do is they store electric charge for later use. Now you might say, well, how are they different than a battery? Because a battery stores charge for use. But they are, because what a capacitor does is it stores the energy and you can use it very, very quickly. Unlike a battery where they tend to discharge slowly. You want a battery to last a while. But a capacitor often you use for things you want to use quickly, like a camera flash. So a camera flash on a cell phone camera or digital camera, or even not so much the old school ones, but ones that have an actual bulb. What a capacitor does is it stores positive charge on one metal plate, just like a little square or rectangle of metal. And we'll see how they're really shaped in the next video. And the other side stores negative. Then when you hit the button, when you close the circuit, that charge can flow. Now, only electrons move. Positive charges are the protons. They never move. But we'll see next chapter when we talk about current, how that really works. So for camera flash, you want it to happen all at once. You want it to happen in a fraction of a second. You use a capacitor. Energy backup in computers. There's always times where there's surges, and maybe you've had this where your computer turns off for a second or two because there's an electrical issue, and then it comes right back on. Well, what computers do is they have some capacitors in there to temporarily store some of that electricity. So if you have that power problem, you don't have that. There's some current that can flow. And in the same way, if you have a surge protector, a lot of power strips with multiple electrical outlets on them have capacitors in them, so that what they'll do is those capacitors are not charged, but if there's a surge, the capacitors will take the charge rather than it going right into your device and frying your computer, or if you're charging your cell phone or something like that. We use capacitors with charges to store the zeros and the one in the RAM of your computer. The RAM is the memory that you can access, random access memory. There's also memory called read-only memory, and that's right on the chip, and you're not able to adjust that. But the RAM you can even change your operating system. All that is stored, uses capacitors and defibrillators. It's hard for me to say, sorry. But, they use defibrillators when people have a heart attack, because what they do is they store a ton of charge, and then if a poor person is having a heart attack, you can zap them immediately and get that charge out really, really quickly. So as we said, the charge is stored on plates, and there's a gap between them. Sometimes that gap is air, and sometimes it's a different material that we'll see later called a dielectric. So they don't want the charges, they can't be connected. If the two metal plates were connected, well, electricity would flow. And what they'll often do is they'll take the two plates, I don't know if I can draw two plates, something like that, almost like a swirl, and they'll swirl them or curl them together. They'll roll them up to try and increase the surface area. So a lot of capacitors that you see and you might use in a lab will look like a little can or a little jar, because inside there it's rolled up. They're trying to increase the surface area. The more surface area, the more charge. So if you can imagine taking like two pieces of aluminum foil, maybe put a piece of paper between them, and then you could roll them up really tightly.